The parallelogram rule is one of a number of ways to solve problems using vectors. In this particular case, we have two forces that are acting on a hook, 150 newtons and 100 newtons, and their angles are given here. And the question asks to resolve those two forces into one using the parallelogram rule. The first step here is to start with a working diagram. In your working diagram, the first thing that you need is a sign convention. The sign convention determines which way is positive y and which way is positive x. Second of all, you need to label all your forces. So I'm going to call this F2, and I'm going to call the 100 Newton force F1. I'm also going to label my angle, so I'm going to call this 10-degree angle beta, and I'm going to call this 15-degree angle alpha. In order to use the parallelogram rule, here's what you do. You take one of the forces, in this case I'm going to take F2, and you slide it parallel over to the tip of F1, and you redraw it. After that, you take F1 and you slide it parallel up until you get to the tip of F2. So here is a line that is parallel to F1. The resultant force will then be the diagonal between those two projected lines. Although you can call the resultant force anything you want, it's a variable, so you can call it whatever you want. I tend to call it FR for resultant force. Now, in addition, there's a couple additional angles that we need to solve for. In order to solve this problem, I will need to know the angle that I will call gamma. Gamma is right here between F1 and F2. I will need to know phi. I will need to know this angle that I will call theta, which is the angle between FR and the x-axis. I will also need to know epsilon, which is this large angle here. And last but not least, I'm going to go ahead and label delta over here. Now delta is the same as gamma. So at this point, before we actually go on and solve the rest of this problem, there's a couple of these angles that we need to know. First of all, finding gamma is fairly simple, and I'm going to do this in what I call an aux-comp. An aux-comp is a format-free zone. I don't grade format within the aux-comp, but your answers still need to be right. Examples of things that go in an aux-comp would be angles, as I'm going to do here, calculating weight from mass. Sometimes distances would go in an aux-comp. The only restriction on an aux-comp is that your answers may not go inside an aux-comp, so I could not solve for FR inside of here. But I will solve for gamma. So if we look at our angle gamma, first of all, between the x and y axes, which are blue here, I have 90 degrees. I already know that alpha is 15 and beta is 10, so gamma is the remainder. So gamma would be 90 degrees minus beta minus alpha. So that means my gamma equals 65 degrees. Now, I will also need to figure out what this epsilon angle is. Epsilon is the angle between F2 and F1's projection. It's also the angle between F1 and F2's projection. They're the same on both sides because it is a parallelogram. And from our geometry rules, we can learn that there are 360 degrees inside of a parallelogram. So all these angles, epsilon plus delta plus gamma, should equal 360. So I can say that epsilon equals 360 minus 2 gamma, because gamma and delta are the same. And that would tell me how many degrees are left over between epsilon and the opposite angle. That's, however, 2 angles, so in order to determine the total that epsilon is, I need to divide that answer by 2. And when you do that calculation, you're going to find that epsilon equals 115 degrees. I'm going to continue this problem with Roman numeral 2, and I'm going to go ahead and solve for the magnitude of FR. And I'm going to say how I'm going to do that using the law of cosines. It is best practice to say not only what you're solving for, but how you're going to solve it in each of these Roman numeral titles. So FR then equals, okay, the law of cosines is the square root of, now we're looking at this triangle right here, the triangle that's made by FR, F1, and the projection of F2. So that's the triangle, it's half the parallelogram, okay? And FR equals F1 squared plus F2 squared, that's the two sides, other sides of the triangle, minus 2 times F1 times F2 times the cosine of the angle opposite FR. Now if we look at this particular triangle, here we've got FR, here we've got the F2 and F1. The angle opposite FR is the angle that does not touch FR, which is this angle right here. I don't have it labeled, but it is epsilon. So that's our equation with our variables with the unknown solved on the left side. Now I'll rewrite that same equation with our numbers. You need to make sure that you include units in your equation and that you correctly include parentheses. So F1 is 100 newtons. 100 newtons squared is very different from 100 square newtons. Plus 150 newtons squared minus 2 times 100 newtons times 150 newtons times the cosine of 115 degrees. And when you plug those into your calculator, you will find that FR equals 212.553 newtons. You then underline that answer 3 times, and we are finished with this part of the problem. Once we've solved for the magnitude of FR, then we can go ahead and plug that value and we can solve for the angle. So this is step 3. I've left the diagram up there just so you can still see what's going on, but normally you wouldn't redraw the diagram again. So we're going to say solving for direction theta using law of sines. So first of all, you'll notice theta is the angle between FR and the x-axis. That is how you're required to report all answers in statics with respect to the x-axis. However, I can't actually solve for that directly. What I'm instead going to first do is solve for this little angle phi here, and then theta is phi plus alpha. So if I were to solve this problem, I would say, using the law of sines, that the sine of phi, and remember the law of sines says the sine of an angle divided by its opposite side. So phi is here, the opposite side is directly across from it, which is the projection of F2. That equals, we know epsilon and we know FR. We already know that epsilon is across from FR because we used that earlier when we did the law of cosines. So we're going to rearrange this equation to solve for simply phi by itself. And you will find that phi equals the inverse sine of the sine of epsilon times F2 divided by FR. You'll notice I skipped some algebraic steps there. You are welcome to write them all out if you feel it necessary, if that helps you. So phi then equals the inverse sine of, well, that's epsilon is 115 degrees. F2 is 150 newtons. And FR was 212.553 newtons. And so you will then find that phi equals 39.7612 degrees. Underline the answer 3 times. Now at this point we do not quite have the answer yet. We have phi, we do not have theta. However, I mentioned earlier that theta is just alpha plus phi. As always, we need to have 3 lines for any equation: the equation with the variables, the equation with the numbers, and the answer. So theta then equals 54.7612 degrees. And now in the answer box, so FR equals 212.6 newtons up into the first quadrant at theta equals 54.76 degrees. The only last thing I need to note is that although we didn't actually use phi in our answer box, it still gets underlined 3 times. Anything you calculate in the GFSA format gets underlined 3 times, whether it's part of the final answer or not.